Like they original comes up every year. Owners are gonna buy that. I'm waiting for it now. Everyone's waiting for it now.
He's gonna hire football tech.
As the quarterbacks?
No, it's a coach.
Yeah.
Get him in the right mindset. I mean, Dak Prescott's a good quarterback.
Every year. Same thing.
That's what the Bills will. Hopefully, get Chiefs. Good team. We're finally at home too. It's great. We've been playing them on the road for so long.
Did they actually, was, I saw the videos of them shoveling a Bills stadium.
Oh, yeah.
That was home.
That was at home. Yeah, last week we were too. For this one too. Because we're the 2 seeds, we get 2 home games a week. Yeah.
Shoveling.
All right. Welcome back, guys. Hopefully you guys had a nice break. So we're starting the second part of unit 4. You guys picked up, or the integrals unit, you guys picked up the packet and the calendar, which is the same as the last one. I just wanted to give you another one in case the other one was attached to the previous packet. And the homework pages. I forgot to include the homework pages in the packet, so that's why it came out as a separate packet. So we're going to go over definite integrals. So this is now going to replace what we did with the limit definition. So limit definition, you guys demonstrated that ability on your quiz, and now we have a much more efficient way of getting to the area rather than going through the whole limit definition. Then we're going to work on average value theorem. The first and second theorems of calculus, we'll do that tomorrow. And then Friday, U substitution. So U substitution kind of acts as chain rule from an antiderivative perspective. It's kind of like going through chain rule, but putting things back together rather than multiplying by an inside outside derivative. So we're going to go through that process. Spend about 3 days on that. And then we'll do test review Wednesday, Thursday, and then chapter 4 test, non-calculator portion. And then we're going to look at some very specific kind of free response type questions that is calculator active. So we'll spend a couple days on that, and then we'll take the calculator portion. This will only be 3 problems, and it'll be like 3 FRQs, but very specific types of FRQs. We'll practice those types. And so these will count as 2 test grades. Okay, 2 separate test grades. Yeah.
Is what we're doing this week needing calculator?
We are going to start introducing what calculators can do for us, but this first test will be non-calculator. So we'll start introducing calculator before that Monday. Right. Okay, so that will take us to the end of this unit, and after this, we just have 2 more units to go. We have units 5/6. That was going to go as one with differential equations, and then the last one is area volume. And that'll take us in March. So that'll be the last one.
So the majority of the material in this packet will be like mostly in the non-nuclears.
Yes, that's right. But I will still give you a test review packet after we get through the notes here. So I'm going to give you a test review packet. Yeah, that has both sets of reviews. Okay. All right. So let's go to page 1.
Yeah, question. These are so the same. Yeah. So
You test it from 1 to 6. If it works, then that's good. Yeah, just test it out. Yeah. Okay, so this is called the first fundamental theorem of calculus. We have two of them, two theorems of calculus. We'll do the second one tomorrow. So this first one says that if I take the antiderivative of a function, whatever that may be, so far we've only had two rules to take the antiderivative. We have power rule, and then we've had our trig rules, right? Our integral trig rules that we learned from the derivative perspective. You guys did that on your quiz. So this notation just says, I'm going to take the antiderivative, and whatever that antiderivative ends up being, that's represented by capital F. So capital F just means, okay, I took the antiderivative, and that represents that expression. And then we plug in our upper and lower bounds, f of b minus f of a. So when we do that, we are actually taking that area finding formula, and we're actually converting it, transforming it into a number, and that number will tell us the area of a region. So this is how we're going to use the antiderivative to help us get to a number which will relate to the area of a region. Okay. So far, we've just been doing what we call indefinite integrals without bounds. But now that we have bounds, we have a left and right endpoint that's cutting off or creating a region for us and allowing us to find the area. Okay. So we'll go through this process. We'll practice this process today. But from a understanding or big picture standpoint, let's recall a couple of things here. So from first semester, we learned that a derivative is a slope finding function. So for instance, if I found f prime being 2x plus 1, you know 2x plus 1 is not going to be a specific slope at a point. It just tells us a formula to get to that slope. So we call that the derivative. And then when we convert that derivative into a number, then we can actually get to the slope. Right? So we can use the formula f prime to get to a specific number that correlates to the actual slope at a specific value. Likewise, the indefinite integral is an area finding function. So if I take the antiderivative of 2x, I get x squared plus c. This is an area finding formula, but I haven't found the area of a region. I just created a formula for that curve. And then the definite integral is finding the actual area. This is where we're going to involve the bounds, plug in the bounds, and get a number. Okay, so if the function is continuous on the closed interval, then the function is able to be integrated on that interval. So as long as our function is continuous, we're able to apply this process and get down to a number. So let's look at some examples here. First example, evaluate the definite integral from 1 to 4 of 3x squared plus 4x minus 1. So the first thing you do is, if you see the bounds, you're going to ignore them, okay? So ignore the bounds to begin with. I know that you're going to be tempted to want to involve the bounds because we read from left to right, right? So if you read from left to right, your natural tendency is, oh, okay, I got to take care of these numbers before I deal with this expression, but it's the opposite, okay? The bounds will be the last thing that we do. So we're going to pretend like we don't see the bounds, and we're just going to pretend like we're going to do an indefinite integral to begin with. Let's do something that we recognize how to do. And then after this process, then I'll talk about how the bounds is going to play a role. So integral of 3x squared plus 4x minus 1. We can go through power rule, right? What is 3x? Now, are all these terms ready for power rule? Yes, right. No radicals, no denominator variable, no parentheses to expand. So we go through power rule 3 times. 3x squared becomes what?
3x cubed over 3.
Which we know will reduce. We'll take care of that later. 4x becomes minus x. And normally we would have a plus what at the end? Plus C. Okay, we're going to leave that plus C out because we're now going to involve the bounds. All right, the plus C, we can have it, but eventually it's just going to go away. It'll just wash out. We do it for indefinite integrals, but for definite integrals, we're trying to get down to a number, and we don't need that plus C anymore. Right? The plus C is just to create a family of solutions, but there's no need to worry about a plus C. Now, what we've done here is we've converted it from lowercase f to uppercase f. Okay, so just want to kind of talk about the notation here. So that just means that, you know, we went through power rule, we converted it from an expression to the antiderivative. Okay, so now we're now sitting in the uppercase f notation. Right. So what we're going to do is I'm going to clean this up here. This can clean up to be what? So now we're sitting at the antiderivative. We're now going to work with this to help us get to a number, which will relate to the area. Okay. So now we're going to take part in this role here. We're going to do f of b minus f of a, and that just means I'm going to take the upper bound and lower bound, insert into each of these functions, and get those values, subtract it, and I'll get my number, my answer. So the way that we're going to do it from a notation perspective, we're going to do a half bracket like this. This tells me that I'm about to evaluate this uppercase f between my two bounds. So I have my lower bound 1 and my upper bound 4. Now, based off of this formula here, guess what number I'm going to plug in first? The upper bound. Okay, the upper bound is going to come first, minus then the lower bound. So I'm going to keep referring back to this formula because this is what we're applying. Okay, so upper bound into the expression. So 4 gets inserted in for all the x's, one by one. Okay. What's the operation after this? We took care of uppercase f of b. Now we do what? Subtract. Okay, so we're always going to subtract next. So minus. Now, what happens after this? Plug in the 1. Now, there's something I want us to be careful about is that this 1 is going to represent f of a, but there's a minus sign out here. So to protect that, what comes after the minus sign, I want to put a big parentheses just as a way to protect this value. We want to make sure that we want to take care of this whole mess before we evolve that negative. If we don't put the parentheses there, you may be tempted to do something a little bit out of order. So I like to always protect this second region after a minus with a parentheses. Okay.
You did evaluate what's inside parentheses first, right?
Yes, yeah, that's what I would do. Okay, so what do we do after this?
1x.
Yeah. So well, the 1 goes in for the x, so 1 cubed.
Oh yeah.
Okay. Plus
1 squared.
yeah. Minus 1. Okay. So 1 plus 2 is 3. 3 minus 1 is 2. All right, so this ends up giving us 96 minus 4 is 92. 92 minus 2 equals 90. Now, this number is an area-related answer. The reason that I say area-related is because it depends on where the graph is. If the graph is above the x-axis, then this is the area. But if it's below the x-axis, then we have an accumulation of negative, positive, negative values. We have displacement. We don't necessarily have area. Okay, we're not going to talk about the area formula until 2 units from now. But for now, we can just have an idea that, okay, this is potentially its area, but we just know that it's area related. Okay. But basically, this is going to take the place of what we did with the limit definition with area, where you got to do that, you know, width times f of a plus width times I. We're not going to do that anymore. Okay, we have a much more efficient way, and this is the more efficient way of getting to our area that we're looking for. Okay, we take the antiderivative like we normally would. Okay, pretend like nothing has changed, and then after you get to your answer, instead of putting a plus c, you're going to have a half bracket with your lower and upper bound in place, and the upper bound gets inserted first. That's the uppercase f of b minus uppercase f of a. I do want to talk about how that area limit definition is going to present itself as a multiplication problem on the AP exam, but in terms of the process of going through all that mess is not, we don't need to use that anymore.
Wait, memorize this formula.
Yes, yeah, we do need to know this, yeah. But really, you're just thinking, oh, I'm taking the antiderivative, and then I got to involve the balance somehow. So you're just you're taking an additional step past what you already know how to do. Okay. Now, sometimes this can feel a little messy, especially if it's non-calculator, you know, having to do all this calculation. AP exam, typically, they don't care too much that, you know, it's not about just plugging and chugging. Okay, that's really not the purpose of AP exam. So what happens is that, you know, if it ends up being really difficult to manage, you could leave your answer in this form on the AP exam and they would accept it. Okay, this is an acceptable answer. Okay, I will talk about sometimes where we have to go a little further than this, but if it's just numeric values, this is an acceptable answer. Okay. All right. Any questions so far? Okay, so for depth integrals, we don't need to worry about the constant of integration plus c. It'll always wash out, so keep that in mind. Now, the reason why I keep coming back to the idea that it's area related and it's not quite area is because we have to consider what's happening if something is above or below the x-axis. So let's take a look at this problem here. Let's just try this problem and work it out by hand. Okay, so what's the first thing we do here? Okay, in-depth integral, right? The bounds is not going to play a role. We gotta take care of this expression first. We gotta produce the appropriate action before the bounds can play its role. Okay, so integral 2x becomes, yep, reduce to x squared. Ready for my bounds. What do we get? What inserts first? Minus. We get 1 minus 4, which is negative 3. Now, what's strange about this number? So we talked about how this is what related. It's related to the area, but what do you know about area? Okay, and can area be this number? Why? It's negative. Okay, so it is area related, but it's not quite area because we can't have a negative value for area. So let me talk about why this number is showing up. So this is what the graph looks like. The 2x is a linear graph that looks like this. Okay, we're finding the area or the region between -2 and 1. So this is what the graph could be. So here's -2. Here's 1. Okay, so between the x-axis and the graph is what this number is telling us information about. So I'm going to shade that region. So here, these are accumulation of negative y values. It's finding that area here, but it's in the negative region, so it's going to give you a negative result. This is the positive result, but there's more region below the x-axis and above the x-axis. So when we do that, we get -4 plus 1, which is -3. So there's portions of the graph below the x-axis that's going to result in a negative value. So we really call this a displacement number, which just tells us that it's accumulation of the positive and negative y values, but there's more negative y values or more negative y value accumulation than positive ones. So that's why we're getting a negative value. Now, there's a way around this to force it to be a positive number, but for now, we just know that a depth integral gives us an area-related value, but it may not be what we consider area. But it's still an accumulation of values. We don't want to, but when we get down to actually finding the area, we will deal with that formula later. But if the whole graph is above the x-axis, then yes, then the number that we get will be the area. Okay, any questions? All right, let's go to next page. Now, here are some integral properties that we're going to be working with. Integral properties is just kind of gives us some tools that can help us either break the problem up into smaller parts, or it kind of allows us to see things and allows us to break down portions of the graph a little bit easier. So let's say we had a graph that was this here. Okay. The integral from a to a, let's say this is a right here. So from a to a of f of x, that just means that if I were to find the antiderivative and I want to find the area between a and a, have I moved at all? I have not moved. So if I haven't moved, so there's no width. If there's no width, there's no area. So if my bounds are the same, there's no width. So area equals 0. So whenever your bounds is the same value, then you can just quickly, even without doing anything with f of x, you already know your area or your antiderivative value is going to be 0. Okay, next up, this is a useful property whenever you're trying to read the graph. Sometimes your bounds may not be in order from smaller to larger. And to help see things a little bit more clearly, you can always change the order of your bounds. But whenever you change the order of your bounds, you have to make an adjustment. And the adjustment is that a -1 has to be pulled out in front. Okay. So if a bound is out of order, I can always flip the bounds, but just know that if I take an action here, I'm changing the problem. And to adjust for that change, I got to make sure I have a negative in front. And the third is a property, sorry, there's a stray negative sign here. There shouldn't be a negative right there. It's just the integral from a to b. So let's say c is between a and b. And I want to find the area of this entire region. Sometimes it's easier to break a problem up into smaller parts so that we can see the properties that's provided for us. So we can always split up a larger region into the sum of smaller regions. So the integral from a to b is the same as the integral from a to c, half the region, plus the other half from c to b. Okay, so I want to show you some examples of how these properties can be useful to help us break down the problem into smaller parts and allow us to arrive at an answer more quickly. Okay, so let's say the integral from 0 to 3 is 4. So some region up under f of x, it gives an area of 4. And then from 3 to 6, it gives us a region of -1, which probably means there's more regions below the x-axis than above. Okay, so it says the integral from 0 to 6 is equal to, so we know that from 0 to 6, 0 to 6 is the accumulation from 0 to 3 and 3 to 6. So let me write out that relationship, right? We know this is true even without looking at the area here, that if I want to deal with the full region from 0 to 6, I can break it into two parts, from 0 to 3 and then from 3 to 6, because that is the useful separation that is given to us. Okay, what's the result of this integral here? We can substitute this with what? 4. And what is this equal to? -1. So we can make it 4 plus a -1, and that's equal to what? 3. Okay. So we're just finding what the numeric value of this. We can't quite do the antiderivative. We have to rely on the properties here to help us get down to the answer, because we can't take the antiderivative. We don't know what the function is. Okay. All right, part B. We're trying to find the integral from 6 to 3. Now, we don't have the integral from 6 to 3 in our property, but we do have what? What's something given to us that's related to this? 3 to 6. So if 3 to 6 is -1, then from 6 to 3 must be what? 1, because we know we can flip the bounds and we can just take the negative. They're going to be the same, but one is just going to be the negative version of the other. So I can say 6 to 3 is the same thing as the negative version of 3 to 6. And if I know this is true, I can replace this portion with a -1, because that is the property value that we have. Now, we don't have to go through all these steps to show. If you understand that this is this different sign from that, you can just jump from here directly to here. Okay, part C. What do you think this one is? Not 1, 0. Yeah, so here I'm going from 3 to 3. I start at 3, I end at 3. I don't have a width to show. My width is 0. So my width is 0. My area is certainly going to be 0 as well. Now, part D is a little misleading. I want to talk about part D here. This +3 is not independent. Okay, this +3 is inside this umbrella of this integral. Okay, so we don't want to treat that +3 as just a +3 on its own. It's within this formula here. But what we can do is we can separate this into two smaller problems, because this is kind of a messy problem to evaluate. But as soon as I have that plus sign, there's nothing preventing me from separating this into the sum of two integrals. So I'm going to write this out. Okay, I can make this even easier for me to evaluate, because where can I put that -5? Outside. The reason why we would want to do that is because if I pull that -5 outside, I can begin to clearly see that I do have something that I can replace with that notation, right? So this one is a pure substitution. We don't do any calculus operation here. We can replace this with what? What do we have available that we can replace this with? -1, right? -1 times -5 is what? 5. Okay, so that's easy to evaluate. Okay. Now this is a different process. Anyone know what we do with this problem here? Can we work this out by hand, or do we need to rely on the property? All right, so this is one that we can work out by hand. Okay, what rule can we use for this? Okay, we can use power rule. All right. Okay, so we said that the first thing we do is we ignore the bounds, right? We just treat it like the bounds aren't there. What's the integral of 3 dx? What's the antiderivative of 3? 3x. Yep. So in a separate space, we got to take care of this issue. 3 becomes 3x. Okay, we took the antiderivative. Now we can do what? App bracket, yep, and then plug in the upper and lower bound. Okay, what gets evaluated first? Yep. So 3 times 6. Then what? What's the operation here? Minus, yep. So it's f of b, uppercase f of b minus uppercase f of a. So minus 3 times 3. What is the result of this? 18 minus 9, which is 9. Okay, so now let's put the two parts together here. We know that this integral from 3 to 6 is equal to -1. So it's -5 times -1 plus 9. So we're kind of dividing and conquering, right? We're taking a messy problem, breaking them up into individual parts. One portion requires a certain way of evaluating. The second part requires a different way of evaluating. But ultimately, we came back with answers from both sections, and now we can add them together. And our answer is what? You mean this subtraction here? Because of the previous page here. Once I take the antiderivative, I always do f of b minus f of a. I'm always subtracting between my upper and lower bounds. Right. What's my result here? 14. Yeah. All right, any questions here? Okay, let's look at example 4 here. And before we look at example 4, let me highlight the first theorem again and how we can adapt that for different scenarios. So we know that the integral from, I'm going to use the space here. We're not going to need a lot of space for example 4. So I'm going to just step to the side and talk about something here. We know the integral from a to b of lowercase f becomes what? Antiderivative of lowercase f becomes, previous page, what notation do we use? Uppercase f, and then we do what? B minus f of a. So we transform lowercase f to uppercase f to indicate that we found the antiderivative. Now, what if I had a notation that looked like this? Integral from a to b of f prime of x dx. Okay. This is an adaptation of the of the theorem, but we can still apply it using a different starting notation. What do you think the antiderivative of f prime will turn into? Well, what's the antiderivative of f prime? F of x, right? Because remember, antiderivative, we're going backwards, right? We know that f becomes f prime derivative-wise, but antiderivative-wise, f prime turns into f. So we can turn it into f because we took the antiderivative, and then we can do what? F of b minus f of a. And we're just adapting this to what the rule says. Okay, let me give you another scenario here. What if I had the integral from a to b of f double prime of x dx? What's the antiderivative of f double prime? F prime. And I can do the same thing, right? F prime of b minus f prime of a. Okay. There's a lot of different variations of this, but we understand the process that we're just taking a function, making it go one level above, and then plugging the upper and lower bounds. So there's no need to memorize these. It's just if you understand the process, then you can do a lot of different variations of this, and it should make sense. Let me give you one more scenario here. What if I have the integral from a to b of the acceleration dt? What's one level above acceleration? Velocity. So I can just say v of b minus v of a. So I don't want us to think that, oh, I got to memorize all these versions. If you understand the process, then if you memorize one, then you can use that to adapt a lot of different scenarios, and you're essentially applying first theorem. All right, let me talk about how that applies for us here. It says the integral from 3 to 8 of f prime of x equals 10, f of 8 equals 6, and find f of 3. So this feels like there's a lot of pieces here. Why don't we create a relationship between these parts, and then we can kind of just make substitutions. So f of tc means first fundamental theorem of calculus. Reminder that f of tc can be used as an equation solving tool to find the value of an antiderivative at a specific point. So we know that this is true, right? The integral from a to b of f prime is equal to f of b minus f of a, right? We're taking f prime, making it rise up to fb minus f of a. So if I adapt it to this problem here, what's my a and b value? My a is what? 3, and my b is, okay, so I'm going to set it up using this formula first for this problem, and then I can worry about how this plays out once I trying to find f of 3. So we can say the integral from 3 to 8 of f prime of x dx. So don't look at what's given to you. Let's just get this into a notation that we can use. Right? F prime becomes what? And then we plug in what? Yep. What's my b and a? Yep. So I can say f of 8 minus f of what? F of 3. So now that I have this in front of me, I know this must be true because this is the relationship between f prime and f and the upper and lower bounds. Now I can make a substitution, right? I can replace this piece with what? Ten, yeah. So this is equal to 10, right? So I can just make a clean substitution. This whole thing is equal to 10 equals, what's f of 8? 6 minus f of 3, right? I don't know what that is. I'm trying to solve for f of 3, so I'm just going to leave it as f of 3. So now, do we have enough to solve for f of 3? Yes. Right. So I'm going to subtract the 6 over. 10 minus 6 is 4. 4 is equal to negative f of 3. So that means what? F of 3 must be equal to, yeah. Okay, example 5, it says the area of each region is given. So this is an area of 10. This is an area of 2. This is an area of 3. But the antiderivative, we have to make an adjustment, right? This is all above the x-axis. So this is all going to come out as a positive 10. That's fine. This is above the x-axis. So this area of 3 matches the antiderivative accumulation of positive y values. This is an area of 2, but the integral of this region is actually going to produce what? Produce a negative 2. So if I want to find the integral from a to b of f of x, I have to make that slight adjustment and say 10 minus 2 plus 3. So if we want to really kind of spell everything out, we can say, okay, the integral from region from a to d can be split up into 3 parts. Integral from a to b, integral from b to c, and integral from c to d. I know integral from a to b and c to d are clearly above the x-axis. That area is going to translate to still be positive, but the area of 2 is going to translate to a negative integral because we have these are all accumulating negative y values. So it's 10 minus 2 plus 3, which is 11. Okay, I want to have us try a problem here, not create any space in your packet. So let's go to the very back of your packet. There's an empty page there. Okay, so we're going to use some properties here. Okay, so part A, let's ignore the 2 for now. Let's just focus our attention on this 0 to 6, right? I could take that 0 to 6 and think of it as what? Yeah, 0 to 3 plus 3 to 6. Okay, 0 to 3 is can be replaced with what? 3 to 6 can be replaced with positive 2. We know that the bounds getting flipped will just cause my result to change signs. So now I can add together and involve the 2 at the end. What do we get at the end? 2 times 7, 14, right? Yeah.
Why wouldn't it go negative?
Well, because the bounds are flipped here. So we know from 6 to 3 is -2. So therefore from 3 to 6, my result's going to be a positive 2. I change the bounds. The bound change is going to be the opposite of that value. Okay, part B, we can think of this as what? Separate problems, right? Separate problems. One problem will be property, and the other one will be its own rule. Okay, 3 to 6, we already know what's that equal to? 2. And this we can use what? Power rule. 4 becomes, or integral 4 becomes 4x. What gets evaluated first? Okay, 4 times 6, then minus 4 times 3. 24 minus 12 is 12. Okay, so let's put everything together here. 2 minus 12 is 2. Okay, how would you handle part C?
Six over three with the 4 would it turn into a positive because don't you have to make it like negative to get the 3 over 6?
Well, this one, we don't have to use the property because it's a standalone problem. It's not f of x, right? This one you just do power rule. So this is completely unrelated to this. Because this, we had to rely on the property because we couldn't do this by hand. But 4 is an independent problem. It'll become power rule. Okay, how about part C here? It looks complicated, but what's nice about this problem? The bounds are the same. It doesn't matter what all this messiness turns into. I have no width. If I have no width, my area is always going to be 0. Okay, check your calendar. Your calendar has your homework from 4.3 and 4.4. And then the other handout includes the homework pages. All right, come get your phones. Yeah.